Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azmi from EC1104K from Group 1. So today I will be present about our project ecs246 about civil engineering material. So the sustainable material that we choose is aggregate. There are two types of aggregate, which is coarse aggregate and fine aggregate. Okay, next we will go to introduce our group member. Okay, first we have Muhammad Azmi. Yeah, that's me. The second one we have Ni Ahmad Fatih bin Suhaimi. The third one we have Ahmad Kamar Arif bin Kamaruddin. And the next one is Ahmad Dani Hakal bin Amran. Okay, for the table of material, the first one we have introduction that briefly explain about the detail of the coarse and fine aggregate. The next one we have a methodology that explain about the procedure towards our replacement tree material that we choose to replace with the regular aggregate. Next, we also have a result and discussion that shows the result from methodology that we test to the tree replacement material that we choose before. Other than that, we also have conclusion about the material that we choose, either it's good or not. Next is recommendation of the material to conclude which of them is good to be used in the future or now. And the last one is reference of our research. Okay, without wasting any time, we'll go to the introduction that presented by me. Okay, so let's go. Okay, basically this presentation is to determine the most possible sustainable material that can be used to replace the regular aggregate in the construction. Construction aggregates, or simply aggregates, are a broad category of a coarse to medium grain material used in construction, including sand, gravel, crushed stones, slag, recycled concrete, and synthetic aggregate. This shows how important aggregates when doing construction. In order to say, there might be something in future that can be used to replace aggregate for better experience in construction work. Okay, next I will introducing our replacement material that we choose to replace our sustainable material, that is aggregate. Okay, for the first material, we have a recycled rubber tire. For the second material, we have a recycled asphalt pavement. And for the last or the third material, we have a recycled fly ash. Currently, sustainable development and environmental protection have become important goals of modern society, especially in the construction industry. In this context, the main problem facing the building material industry are mainly related to the decline of natural aggregates, high consumption of Portland cement, and high carbon dioxide emissions, construction waste and demolition, and the exhaustion of landfill space that can lead to the problems such as pollution, natural disasters, etc. Concrete is often chosen in construction because the raw materials are cheap and easy to find. However, the immediate consequence of using concrete is to consume too much aggregate, leading to the depletion of the natural resources of the aggregate. Humans need to find other options to get the set. One of them is to use used rubber tires, because every year a large number of tires are produced without adequate solutions to deal with the huge amount of rubber waste. In addition, numerous studies have shown that concrete containing rubber aggregate has a number of interesting properties that favor its use as a building material, which are sometimes very different from standard concrete. The growing emphasis in the construction industry on the sustainability is leading to an increasing use of recycled aggregates in pavement layers. The use of reclaimed asphalt pavement, or known as RAP, is becoming increasingly popular with asphalt manufacturers due to the ability to partially offset the virgin bituminous binder with the binder from RAP aggregates. In order to maximize the amount of substitution of the bituminous binder, asphalt manufacturers almost exclusively use fine fraction, thus large stock of raw RAP are created, although the use of RAP as a synthetic source is a sustainability practice. It requires pure synthetic manufacturers to supply synthetic source with reduced fines. Quarry byproduct QB, the finest fraction of aggregate extracted, currently comprises 8% aggregate extracted with little use. The use of RAP or QB in pavement layers has been studied in the past by many researchers. However, the use of either of these recycled marginal materials in cement, threatened foundation has been dropped in a somewhat limited way, especially the use of QB. Globally, the concrete industry consumes a large amount of natural resources which are becoming insufficient to meet growing demand. At the same time, many old buildings at the end of their useful life are demolished, causing wasted concreting. Some concrete waste is used as landfill material, and much of it goes to landfills. Recycling concrete by using it as a new aggregate in concrete can reduce concrete waste and serve as a natural source of aggregate. Many studies have tried using recycled aggregate in engineering and have found that it reduces the compressive strength in concrete. Due to the low compressive strength and workability of concrete containing recycled aggregates, most previous studies on recycled aggregates in concrete have focused on replacing coarse or fine aggregates and have been limited to a low degree of substitution for recycled aggregate. Several methods have been used to improve concrete containing recycled aggregate.
Okay, the next slide is methodology. The first one is completely wash rubber with pure water and carbon tetrachloride solvent, and water with latex as mixture cleaner. Second is using two different types of cement, magnesium oxychloride cement and Portland cement, into the washed rubber. Number 3 is all data were classified in terms of replacement of fine aggregate, replacement of coarse aggregate, and simultaneous replacement of fine and coarse aggregate with varying percentage of rubber. The last is combine all the concrete and rubber together into one container. Okay, next slide. The next slide is methodology. The first one is prepare fabricate from a 150 × 300 mm cylinder. Number 2 is specimen were loaded at a crack mouth opening displacement CMOD rate of 0.06 mm until the specimen reached a peak load. Number 3 is the specimen was reloaded at the initial CMOD rate until failure. Number 4 is the clip gauge used to measure CMOD has a maximum opening of 6.35 mm. The last one is the test was stopped at a CMOD of 5 mm for specimen with fiber. The next slide. The next slide is methodology. The first one is prepare the fly ash and grinder. Number 2 is the fly ash was ground until the particle retained on a sieve for 45 mm opening were 1.2% by weight. The last one is the ground fly ash then used as a pozzolanic material to partially replace Portland cement.
Assalamualaikum warahmatullahi wabarakatuh. So today I will explain about the data and the discussion about the replacement of tire in the mixture. So this section investigate the reduction of compressive strength of rubberized concrete mixture in terms of the rubber content. SRF, or known as strength reduction factor, can be used as a guide for the procedure of a mix design to predict or to calculate the amount of mixture and the setting condition for the starting mixture design in order to get the required performance for the mixture. So, what is strength reduction factor? Strength reduction factor is can be defined as the ratio of the compressive strength of the rubbercrete with a certain percentage of rubber to the compressive of the concrete without rubber. So, in the tested mixture, the percentage of rubber refers to the total of volume of aggregates. So, there are formula that we can use to calculate this, or we can define as SRF is equal to A plus B 1 minus X to the power of M, where A plus B is equal to 1 because of the characteristic function must be decreased with the increase of percentage of the rubber, and the maximum value for rubber when the rubber content is 0 is 1. So the figure that on the screen shows the value of concrete compressive SRF with respect to the percentage of the volume of the natural fine aggregates substitute with the fine aggregate. The presence of voids in crete affect the density and greatly reduce the strength of the concrete. So, due to the very low value of elastic modulus of rubber aggregate compared with that of natural aggregate, the rubber aggregates can be assumed equivalent to voids. Although rubber particles cannot be physically equated with voids, the elastic modulus of rubber particles value are also near or in a range with ordinary concrete. Then I will explain about the asphalt pavement when we use it in a mixture. So, a modified prototype compaction testing was used to determine the moisture density relationship for each mixture. The maximum dry density and optimum moisture content of each mixture were used to determine the final mixture proportion as the given table. So the table that given below is about the flexural performance testing result, where load versus deflection curves for the fiber reinforced mixture. The table below shown about the 3 beam specimen have been tested. Increasing cement content lead to significantly greater values of peak flexural strength, residual flexural strength, and flexural toughness. And cement content did not have a statistically significant effect on equivalent flexural strength ratio. As expected, the inclusion of the fibers did not have a significant effect on the peak of flexural strength. So the table 2 shows about the fracture testing. The fracture testing was performed at an age of 28 days according to the procedure set forth by Amir Khanian. For the disc-shaped compact tension, or known as DCT geometry, specimens were fabricated from a 150 x 300 mm cylinder, which was compacted according to ASTM C1435. Due to insufficient strength to withstand the saw cutting and coring required for DCT specimen preparation, mix 2RF was not tested. So, as the table 1 show, we use 2RF mix for the fiber mixture. So, as the table 2 shows, the KIC, or known as critical stress intensity factor, is a measure or a guide of a material's initial cracking resistance. And for the mix that containing 4% of cement was statistically greater than the mix of containing 3% cement. Next, I will explain the result of fly ash in the mixture of concrete. So, the graph below show about the slump test for NAC and the recycled aggregate concretes. The initial slump value for NSE was 60 mm, which decreased to 0 at 105 minutes after mixing. Loss of slump was faster in recycled aggregate concretes than in the control concrete, particularly in the sample in which river sand was replaced with RFA. For an example, the slump of AF, BF, and CF concretes decreased to 0 at 90, 75, and 60 minutes after mixing respectively. This might have been caused by the water absorption by the fine recycled aggregate, which quickly reduced the amount of water in the mixture. The fastest slump loss might have been occur due to the fineness of the fly ash, which provided more surface area to react with the water. However, the slump loss of recycled aggregate concretes decreased when the high fineness of fly ash was replaced Portland cement at 35 and 50% by weight of the binder. And the result suggests that incorporating high fineness of fly ash could reduce the slump loss recycled aggregate concrete. This was similar to another experiment who found that fly ash can reduce slump loss when it is particularly used to replace cement. The figure 2 below presents the compressive strength of recycled aggregate concretes. For NSE, after 28 days, the compressive strength obtained is 47 megapascal, and for the same period, AF, BF, and CF concretes that contain recycled aggregate has respectively compressive strength of 44.1, 41.3, and 35.9 megapascal. Therefore, use of 100% RCA reduced the compressive strength of concrete by 6% compared to NSE. In addition, replacement with RFA corresponded with a reduced compressive strength recycled aggregate.
As conclusion, this research looked at certain essential features of concrete mixture that had stone aggregates partially replaced with rubber particles from recycled tires. A greater reduction in concrete compressive strength is expected when rubber aggregate replace coarse aggregates rather than fine aggregates or both fine and coarse aggregates. The resulting material, called rubberized concrete or rubbercrete in the literature, has mechanical and rheological qualities that make it appropriate for civil and industrial purpose, and it is a good way to recycle old tires. But the use of rubber particle as a replacement of fine aggregate should be permitted only under strict quality control procedures, and particularly in percentage of not more than 10%. As conclusion, it can be concluded that the aggregate mix was 70% quarry byproduct, which is UB, and 30% coarse fractionated recovered asphalt pavement, which is FRAP, or 30% virgin coarse aggregate. Furthermore, we know that use of macro-synthetic fibers with recycled and byproduct aggregates, FRAP and QB, respectively, for lightly cement treated layer not only increase the fabric life, but will also maintain tighter cracks, which can reduce reflective cracking of overlying pavement layers. In conclusion, recycled aggregate concrete with a high fineness of fly ash had a higher compressive strength than recycled aggregate concrete without a high fineness of fly ash. At 28 days, concrete made entirely of RCA and river sand achieved compressive strengths comparable to or greater than NEC. At 20% to 35%, cement was replaced by high fineness fly ash by the binder's weight. In addition, concrete construct using 100% RCA, 15% RFA, and 35% high fineness fly ash as a cement replacement exhibited a higher compressive strength at 90 days compared to NEC. Now, I'm going to talk about recommendation. Every year, large amount of tires are created without adequate consideration about how to deal with the massive amount of waste rubber produced. From this research, we are recommending that concrete with recycled aggregates from tire is suitable material that can apply in civil engineering. It is because it has an important role in the sustainable development of buildings, in the reduction of pollution, and in conservation of natural resources and energy saving. Furthermore, rubber aggregates are characterized by a very low modulus of elasticity compared with that of concrete of natural aggregates. Besides, rubber particles have lower strength than the concrete mix around them, and thus, when force is applied, the crack first appear in the contact zone of rubber and concrete matrix. The replacement of natural aggregates with rubber also reduces the Young's modulus, allowing the material to absorb energy with small deformations.